Hello everyone, may I have your attention? The webinar is about to begin in a few minutes. Hello everyone, and welcome to today's webinar, The Etchings and Charge Transport Dynamics in Polyethylene System. My name is Dr. Kanchit Ngamtalot, and I will be your moderator. I'm an executive committee for the IEEE Power and Energy Society Thailand, and working with Electricity Generating Authority of Thailand, IEEPES, as the expert in power plant. I'm very excited to be hosting this webinar today. This is what we call IEEE Power and Energy Society Webinar Series 2020. This is part of the event that conducted by the Technical and Social Activities Subcommittee IEEE-PES Thailand. In this session, we would like to have a presentation on the etchings of charge transport dynamics in polyethylene system from Dr. Somyot Tanti Pipatrarakul. Before the webinar begins, allow me to introduce the speaker. Dr. Somyot Tanti Pipatrarakul, he is an engineer working with transformer maintenance and workshop department for IEEPES. Before I hand the session over to Dr. Somyot, I have a few items to cover about the webinar. The webinar will take about 45 minutes continuously, and we will have 15 minutes for question and answer. If any participant have a question in your mind, please feel free to send it to the chat box on this Zoom. We will be answering your question at the end of the session. I would like to welcome the speaker. and deliver this session to Dr. Somyot. All right, Dr. Somyot, the panel is yours now.
Okay, can you hear me?
Completely.
Okay, shall I start the presentations?
Yes, sure.
I will share the screen first. All right. Do you see the screen?
Yes.
Okay. So good afternoon, everyone. My name is Somyot Tanti Pipatrarakul, as Dr. Kanchit introduced me. Today I would like to present my research project from from my PhD study in the University of Southampton. So this is my education background. I'm just a graduate from the Doctor of Philosophy in Electrical Engineer from the University of Southampton this year. Now I work in the now I work as the Electrical Engineer Level 7 in the Transformer Maintenance and Workshop Department for ECAT. This is the picture for my lab. So the outline for today, I will give you some background knowledge associated with my project. And then we will go to research question and objectives, basic informations and conditions, the characterization techniques that I use to analyze the property of the materials. And then I will show some key results, conclusion and work contributions. So excited today. This is my first time. So the first thing, my project is consider about the high voltage direct current condition for the power cables. So I would like to give you some idea for the HVDC, the growth of HVDC transmission system. In figure 1, this is show the HVDC system already available in the world. They have 4 systems and 2 systems about submarine and land offshore. They use the power cables, HVDC power cables. So in the figure 2, we could see the significant growth up of the HVDC transmission market. That's in 2018, the investment for the HVDC transmission market about 8.2, significant growth up to 12.3 in 2024. This is a show the significant growth up in the submarine cable in figure 3 as well. And this figure is show the underground cable and submarine cables installed at the positions between land to land to the sea. And in the figure 4, we can see the structure of the power cables. Here my project is considered about the aging phenomena for the polyethylene insulation. As all of you know about the advantages of the power cable, I will remind you again about the advantage of the power cable. The power cables can reduce the public concern in the urban areas, as you can see in the right picture. When the Japan, I think this is a Japan country, use the power cables, the messy things about the overhead line to be reduced from the public concern, and then the cable installation is not limited by the land and environmental. As you can see from the right picture, when we use the power cables, underground power cables, the light of way will be reduced for the distance. And then the power cables also widely used in the renewable energy and smart system as well. As you can see from the right picture, that the cable system used for the wind farm, solar farm floating on the sea, and also in the EV station. So the last thing is the power cables The losses in power cables are generally lower than the overhead line. For the aging study, um, there, there are three topics about the aging study that we should know about: the aging mechanism, insulation performance, life assessment. And when the aging initiate in the power cable insulation, it will change the chemical structure from nano to micro scale. After the modification of physical, chemical, and electrical properties, it will lead to the degradation and the failure of the power cables. And this is the research question that I wrote from my thesis. The first question is, what is the aging method and the condition that I need to study? I will show later. And number three, question 3, and question 4. I need to know about the effect of aging on the physical chemical property change and the effect of morphology of PE. Morphology of PEs is mean like I will show in the picture later. For briefly, the morphology is about the crystal and the chain structure in the PE when we see from the scanning electron microscope. This is I want to show the morphology effect on the oxidative rate and forms. For the number 4, actually, when we consider about the aging in the PE insulation, we found that they have two forms. For example, about the form is non-uniform and uniform distribution of aging, and this kind of form will affect the space charge accumulation inside the polyethylene and also charge transport. So the last question is, I would like to know key factors causing an initial decrease in electrical performance. So this is the research objective. I would like to study about the effect of early state of aging associated with the accelerated thermo-oxidative degradation that have an effect on the physical chemical change related to chemical structure, physical structure, and electrical performance and charge transport dynamics. So now we go to aging formation and condition. So the figure 1 show the chemical structure of the polyethylene. As you can see, a lot of chains, a lot of carbon chains in the polyethylene structure, including with the polymer chain and amorphous structure. So after the polyethylene subjected to temperatures, the thermo-oxidative aging process will be promoted, and then resulting in the new chemistry occur in the system. So this is called the aging byproducts. The aging byproducts from the thermo-oxidative aging, normally including with the hydroxyl group, carbonyl group, as you can see in the figure A and B for figure 2, and double bond, figure C, 2C, conjugated bond, triple bond, vinyl. Why I show this chemistry? Because of this chemistry, it affect to the charge transport dynamic and also electrical properties of the polyethylene. but the important chemistry is the carbonyl group, because the carbonyl group is have been widely studied by many researchers that this kind of a functional group significantly affect to the electrical property of polyethylene that might be lead to the failure of the cables. So this is the effect of aging of the aging byproduct to the polymer band structure. Previously, we talked about the many kind of chemistry here in the figure 1a. This chemistry represent themselves at the traps, at the shard trapping site in the polymer band gap. That some of them is a shallow traps, some of them is a deep traps. What's the meaning of the shallow trap and deep traps? Shallow trap is like they could trap the shard in polymers for shorter time than the deep traps. For example, if the electron is captured by shallow traps, it could be trapped inside the polyethylene maybe for microseconds. And for the deep, in case of deep traps, the electron could be trapped for 10 to the power of 12 seconds. That means it's about a month. So this figure 2, show how the shard transport inside the polymer insulation. You can see in the left corner when the electron injected into the insulation system, they could be trapped in a shallow trap here, and then they could hope to the conduction band, participate in the conduction process, and then they could trap to the deep traps that hard to transport. So this kind of the trapping process for the shallow traps and the deep traps can affect to the shard transport dynamic, and then result in the change in the conductivity and breakdown process as well, because of this kind of trapping shard can modify the internal electric field inside the polyethylene. So for the aging condition, as I said, we consider about 2 forms of the aging. In the figure 1, this is the form of the aging in the real cables proposed by some of the Chinese researchers. For figure 1 in the left-hand side, we could see the XRP cables accelerated aging by 100 degrees Celsius for 8,760 hours for a year. And for the right-hand side, this is a cable, practical cables used at 60 degrees Celsius for 22 years. What is different between non-uniform and uniform? You can see from the graph in the middle that show the carbonyl index. As I said, the carbonyl group is the key for for indicate the degree of the aging for the polymeric insulation. So now we can see the non-uniform aging. The carbonyl index is highest near to the conductor core, and then reduce through the outer of insulation. And for the uniform aging, you could see the carbonyl index nearly the same throughout the bout of insulation. And I try to imitate these two forms into the simulate into the polymer sheet. I call the aging regime 1 for the non-uniform aging and aging regime 2 for the uniform aging. And I try to find what is the aging condition for these two forms. So for the regime 1, aging regime 1, I use aging at 160 from 1 to 6 hours. And for the uniform aging, I create the aging at 120 degrees Celsius from 120 to 720 hours. And then I will show how to prove the uniform aging and non-uniform aging. So we go to the characterization techniques. This is the techniques that I use to analyze the chemicals and physical change for the polymers. Number one is Fourier transform infrared FTR spectroscopy. I use to find the chemical compositions in the gaseous polyethylene. Number two, confocal Raman spectroscopy used for analyze the chemical composition in very small area because they use the laser beam in the diameter about 5 microns, something like that. And number three, differential scanning calorimeters used for analyze the melting temperatures and crystallinity of the polyethylene. And number four and number five, this is a microscope. Different in the number four is an optical microscope, and number five is scanning electron microscope. Number five, I used to investigate the morphology structure of the polyethylene before and after aging in nano and micro scale. And number six is gel measurement. After the aging occur in the polyethylene, the polyethylene insulation may have the cross-linking process. So the cross-linking process will result in the gel content in the polyethylene. So I will use a gel measurement to measure the cross-linking percent. And for the electrical characterization, I think the first equipment dielectric spectroscopy normally widely used maybe in Thailand nowadays. So we used to measure the complex permittivity vary with the frequency range from 0.1 Hz to 1 megahertz. And then the second is spatial measurement with the pulse electroacoustic method, we call PA method. So this equipment used to locate the charge accumulated and the charge transport inside the polyethylene. We can locate it, the charge accumulation before the PD occur. Because this is a charge accumulate during the initiation state of aging. And then number three, DC breakdown theta. I will not talk about the key results related to the DC breakdown today. And the first one is conductivity measurement. I will show the result with the change in conductivity varies with the time dependence. For the key results, this is the examples of chemical analysis using a FTIR equipment. This is the results I got from the aging samples contain non-uniform aging concentrations. We could see the figure A. This is a highly oxidized surface, and figure B, lightly oxidized surface. I measure two surface, the change of chemical structure for the two surface, and then I plot the carbonyl index derived from FTR spectroscopy at the peak position about 1700. This peak called the carbonyl group, including with the ketone, ester, and aldehyde group, and the gamma lactones. So we could see in the right figures, the carbonyl index from one surface increased significantly and differently from the non-oxidized surface. Starting from 2 hours. So here we suspected these samples should have the non-uniform aging. So I used the Raman spectroscopy to support in through the cross-section of the polymer sheet that have the thickness about 200 microns. So I measure the chemical change from the surface into the bowl, take the step every 10 microns. So you could see in the figure 2, this is I cut the thin film in the micro scale and then try to analyze the chemical change. In the figure 3, it showed the spectrum obtained from the Raman spectroscopy. And then this is how the aging degree represented by the carbonyl index change for the non-uniform distribution. We could see in the figure A, for the reference samples, this sample is unaged samples, no change for the carbonyl index. It's about 0. You can see from reference 1 hour and 2 hours, there are no change for the degree of aging. And then the aging starts from 3 hours, the green line here, and increase to the 6 hour significantly. For the right hand side, when you use the low temperature for aging for the longer term, the change in carbonyl index confirm that the change of the aging degree through the thickness of the sample is almost the same. That means a uniform aging. So this is the first step to prove the chemical change related to the different kind of the aging condition. And then we look into the modification of physical structure for the left hand side. This scanning electron microscope figures show the homogeneous structure of the sample that's subject to the non-uniform aging. You could see the oxidized surface become crack because of the high oxidation. And for the right hand side, the bowl insulation seemed, as you can see, homogeneous structure here. Everything changed equally in the same situation, same aging degree. And the below figures, the graph is show the crystallinity change with the aging time, with the increase of aging time. The crystallinity will reduce when you aging more and more because of the chain, the polymer chain will be broken by the time. And then this is the highlight of this work. You can see first in the figure 2 for the right hand side, this is the reference samples with the 3 different morphology. For figure A, this is called quenching morphology, that the cable was produced, the insulation materials was produced very quickly from melt. I quenching in the water very quickly. But in the figure B, the crystallization process is very more slower. We crystallize the polyethylene at 115 degrees Celsius for 1 hour. So you can see the white line here in the figures. This is a lamellar structure or the crystal structure of the polyethylene chain that's filling the space throughout the bowl of insulation. And then in the figure C, this is a polyethylene produced with the crystallization process at 124 degrees Celsius for 4 hours. The crystal will be bigger than the other, about 20 microns. And then you could see the black space surrounding the crystal, the white crystal here. This is a amorphous contained with a low polymer chains. So how this morphology important to the aging process? This is a question. Look at the figure 1. We could see that these 3 systems, number A called Q, number B, figure B called 115I, figure C called 124I. You could see that the aging degree increasing by time. The 115, the black line here, have to show the longest aging threshold. That means these materials for figure B, figure 2B, this material 115I have the longest aging threshold, have the highest ability to withstand the aging process. This why? Because of the crystal, this form of crystal prevent the oxygen diffusion higher than the others. Because of if you look into figure 2C, the black area here, the amorphous, is easier allow the oxygen to diffuse into the system. And if you have the more oxygen diffuse into the system, the aging process will go faster than the others. So as you can see, the blue line here, 124I, have the lower aging threshold. Here is about 198 hours. So this slide show if we can control the morphology of the polyethylene insulation, we can control the aging process as well. And then these 3 figures show the morphology change during the aging process. increase with the time. We can see from the every picture, when you aging more time and more time, the structure, the crystal structure will be destroyed. You can see from figure 1 in the middle. This is a crystal structure, look like a circle and circle line here. And then when we aging at 360 hours, no crystal structure shown in the figure 1C. And also if we look into figure 2, aging for 3 hours, 360 hours, the crystal structure that look like circles cannot see in the last in the figure 2C as well. So this is how the morphology changes. And that morphology change can investigated by DSC as well. You can see this melting point in the DSC is related to this kind of a crystal structure as well. For examples, if we look into 124i here, the melting peak here will reflect to the melting of the crystal structure here. It's a big crystal structure. So we can use DSC to indicate the morphology structure as well, to confirm with the SEM's analysis. So the last result is electrical analysis. So first we go to the effect of aging on dielectric response. As we can see from two aging regimes, when we have the aging produced in the system, that means you have several kinds of chemistry represent the dipolar molecule in the system. When you have more and more and more aging, you have more and more dipolar molecule as well. This dipolar molecule will affect to the change of the complex permittivity. For examples, if we look into the figures 1 in the left-hand side, the polarization will be increased, corresponding to the increase of aging. As we can see, the increase of the aging time, and also the imaginary part permittivity increase as well. That means the dielectric loss in the system increase with the increase of the aging figures. So, in specifically, we can see the peak, a little peak here. This peak is relevant to the combined relaxation process. That means you can use this peak to investigate some change of the chemistry as well. So in my case, this relaxation peak related to chain transitions process, and also related to the occurrence of the carbonyl group. Because of this peak linked to the response of the natural frequency of carbonyl group at 10 to 10/2 hertz. Okay, to the next. This is how to separate the combined relaxation peak. I can extract the combined relaxation peak from the dielectric response curve. P1, P2, and QDC IP is mean for the P1 and P2 is mean different process of the molecular dynamics. That means we can use this two peak to analyze what's going on, like what kind of the molecular that have the motion response to the alternative fields. And also QDC is mean represent the conduction, DC conduction that you can see with the severe aging samples here. The conduction process will be involved in the dielectric response curve. And what the dielectric response provide, they provide the footprint of the materials that you can use to analyze the health of your insulation. And then dielectric response can detect the dipolar moieties related to physical chemical change, such as the water contents, oxidative chemistry at ICES, chain transition process, interfacial and geometrical change. And also we can determine the change in dielectric loss and dielectric permittivities that used as a complementary result to compare with the space chart and conductivity results. And this is examples for the effect of non-uniform aging and polarities effects on the conductivity. For the first figures, this is what we test the polymer film. I use the anode in contact with the for the first case, I use the anode in contact with the oxidized surface called AOX case. And for the figure 1B, I use the cathode in contact with the oxidization surface. This is this process. I need to study about the different type of the charge injection into the oxidization layers. So for the left hand side, the result of the conductivity change, we can see a different change in the time dependent of the conductivity in case of the positive injections and the negative injection here. And then if we look into the change in conductivity after aging from 1 hour to 6 hours in both cases of the different polarities, you could see when we inject electron into the oxidization surface, the aging threshold for the conductivity increased again after aging will be shorter than the positive injection. That means if you have the negative polarities used in the cable system, this is become worse than the positive injection. So can be summarized as the aging threshold for the positive charge is higher than the negative charge. And this is a conductivity compare between the non-uniform aging and uniform aging. So you can see the same thing happen after the cable insulation aging. agent from the temperatures. From the reference here, when you have the aging process going on in your power cable installations, you could see firstly the conductivity will be reduced. That means you might think when you test the cable, oh, conductivity is reduced, and this your installation should be good. Yeah, maybe, but the aging process already start in the cables in the polyethylene materials, and then when they reach to the aging test hole, it will be increased significantly and progressively to somewhat level, will be saturated at some point of the aging time. This is a remark for the conductivity change with the aging time. And for the last measurement that I would like to present today is a space chart measurement. For the first, we look at the figure 1 schematic diagram of the PE method. If you see the blue block here is insulations, we can detect the charge accumulated inside the samples by apply the constant DC voltage, and then apply some small pulse into the insulation system to excite the charge trapping in the insulation. And then when the charge was excited by pulse, it will be produce some acoustic sound, and this acoustic sound will go to transducer and then go to the amplifier and go to the computer's program to interpret the data as shown in the figure 2. So look into the figure 2 for non-uniform aging case. For the above figures, we have the polyethylene sheet aging slightly, contain the slightly oxidized layer, and for the below figures, we have the highly oxidized layer. For the right hand side, this is show the space chart result that you could see for the aging for 3 hours, the charge was trapped inside the polymer insulations. This is the size of the traps. When the traps, they will refuse the further injection from the anode. So you couldn't see any change from of the charge inside the insulation after from a 0 minute to 60 minutes. And then in case of the highly oxidation layers present at the anode, the positive injection will be injected through the high density of the traps by the tunneling process and hopping process. So you could see the charge migrate and move very, very fast into the insulations from a 0 minute to 60 minutes. And this very risk. This condition is very risk for your insulation because you could see a positive charge here accumulated near the cathode here. That means you have the very high internal electric field modification in the insulation for this case. So that could be promote the electrical tree aging later. And then in case of the uniform aging, the spectrum result will show in a figure in the right hand side. This is a usual spectrum behaviors for the slightly oxidation and severe oxidation. At from the figure at the right corners, we call this kind of spectrum behavior that called the heterocharge occur inside the insulation. But for the severe oxidation in the figure in the right corner below, this we call the heterocharge. The heterocharge is mean you have the different type of charge against the electrode, both electrodes. Here we can see the positive charge against the cathode. This is a difference between if you have the aging for two form, they have a different result. So after that, we can use this special accumulation result to calculate the trap density that represented by the carbonyl group or any other chemistry in the polyethylene system. And also we can calculate the trap depth energy as shown in the figure 2 as well. So these two figures, this result, we can use to evaluate the life of the insulation as well. That you need to develop some mathematics model to assess your your insulation in the power cables in terms of how many years remaining for using in the system. And for the conclusion, we go for the conclusion. Conclusion, carbonyl group is the key aging markers for this project as well as presented in the many journal papers, which is that concentration reflect the degree of oxidation in PE. Chemical analysis show monotonic change, while the electrical analysis reveal non-monotonic change. This is a disagree between chemicals change and electrical change. The trend is not the same. And then the polymeric morphology clearly affect to the rate of aging and the aging thresholds, degree of oxidation in the polyethylene related to the different oxygen control and diffusion process. And the increasing dielectric polarization and loss correspond to the increase in the degree of the oxidation degrees. The density and distribution of the deep traps represented by the carbonyl group are the key features, as I said, which is determine space charge accumulation and charge transport dynamic. As you can see, the change of the conductivity and space charge results. The formation of space charge are clearly different between non-uniform and uniform distribution of the traps. And space charge measurements is an efficient method to detect the initiation of aging and health of the solid insulation before the aging is developed to electrical tree aging. Electrical property become worsens after aging threshold. Electrical property are strongly influenced by chemical defects rather than the change in crystallinity and morphology. So for the work contribution, This work, we will deeply understanding about the effect of thermo-oxidative aging on the physical, chemical, and electrical property chains. This work can use as the complementary data to aging monitoring, life assessment, design development, and operating decision for the cables, and provide the knowledge base for other analysis, such as the effect of antioxidant. We can use space chart to analyze the effect of antioxidant on the charge transport and any change in the electrical property or moisture content on the materials properties. So this work, I have the reward from the G Kelvin as well in 2017. This is the first prize winner for young researcher contest from G Cables. And the outcome of this project, I have 3 conference papers and 3 publications for the journal paper. In Journal of Applied Physics, IEEE sections on the dielectric and electrical insulation. And the last one is I published in the special magazine IET, Journal of High Voltage Engineer, in a special issue for advanced materials for HVDC insulation. Thank you for your attention. I'm very excited today. If I'm not present in a good way, so I apologize all the audience. Thank you.
Okay. Thank you very much, Dr. Somyot, for your very informative and interesting topic. Actually, I don't want to interrupt your presentation because of the time, but I know that the work that you have been done is quite a lot, but it's quite very interesting. So, all right, and here are the session for Q&A. I'm not sure that if there are any questions from the audience concerning with the aging and charge transport dynamic in polyethylene system. Anyway, I will start from my side first. Dr. Somyot, I would like to ask your the question, maybe the first question. Why is the conductivity suppressed for the low concentration of aging?
Okay, this is a good question. The conductivity is suppressed at the early stage of aging because of the low density of the carbonyl group presented in the polyethylene system. When we have the low concentration of the carbonyl group, this will represent the low trapping size concentration in the system as well. So when you have a very low traps concentration, the injected charge or charge transport in the in the insulation system will be trapped for a longer time than you have the high density of the trapping size, because when you have the very high trap density, the charge transport dynamic will be affected by the hopping process and the tunneling process through the high density of the traps. The charge can be hopped between the traps, and then they could move very easily in case of the high density of the traps. But when you have the very low concentration of the carbonyl group, I mean the low aging degree of oxidation, the charge will be captured for longer time, and they will repel the further injection. So this will resulting in the low conductivity as well, because of the charge transport will be reduced.
Okay. There's one question, very interesting from the audience. Does the space chart measurement are suitable for on-site test?
Okay, this is a very good question as well. I have read one paper and thesis from Delft University in Netherlands. The special measurement can use as the online monitoring for the power cable as well before the PD occur inside the power cables. They use the two electrode make like a cylinder tube to attach and install at the along the cables, and we can slide this kind of tubes along the cables and measure the location of the spare charge accumulated inside the power cables during the operation of the power cables. This is how we can investigate the initiation of the aging inside the power cable before the PD occur.
Okay, I have another question concerning with the spare charge measurement. Is it possible to have spare charge in for AC power cable?
Yes, of course. The spare charge is come from the charge injection from the electrode. So, in case of the AC cables, we have the alternative fields. That means we have the two different charge, positive and negative, injected into the system together. So when they're injected into the system, it is possible for this charge, these two kind of charge, accumulated inside the power cables, but the phenomena, like the amount of the charge accumulation inside the AC power cables will be less than DC cables because of they have a recombination process between those two type of the charge because of the alternative fields. That different.
Okay. There is one question from the audience. The question refers to slide number 29. Slide number 29. Okay.
29.
29.
Page 29, right?
Yes, yes. Slide 29. If I'm right, yes, that's right. 29. The question is, does the fact that the aging threshold for positive charge greater than negative charge, the effect which polarity of the HVDC should be used in the transmission system?
Pardon? Can you?
Does the fact that the aging threshold for positive charge greater than negative charge affect which polarity of the HVDC that should be used in transmission system? I mean, the question is the fact that the aging threshold for positive charge greater than negative charge effect. This is true?
Yeah. Thank you for this. Is a kind of hard question in the quantum physics. So you can see from the negative injection in case of the test hole is about 2 hours compared to the positive charge 3 hours. This means that the increase of conductivity for related to the aging is higher in case of positive charge because of the when the molecular the mass of the positive charge is higher. That means they trap for longer time in the polyethylene. So this means the negative polarity is worse when compared to the positive polarities in use for the HVDC system. Yeah, I don't know this is answers your question or not.
Okay. I know that maybe I will give you this question later, and maybe try to contact the audience that raised this question, and we can explain in more detail later because we are running out of time.
Yeah.
So yes, I think this webinar would be very important to support the reliable course of HVDC development, even in Thailand or in other areas. Maybe somebody will ask about the HVDC development in Thailand, especially with that we are planning to do like a kind of refurbishment of HVDC 300 megawatt in the south. The existing one that are going to like a need to be refurbishment need to be refurbishment on by 2022, and any other new installation with HVDC as well. And there are some what we call feasibility study with the long interconnection from neighboring country by HVDC. So finally, we come to the end part of our IEEE Power and Energy Society webinar. We would like to say thank you again to our speaker, Dr. Somyot from ICAT, and for this very informative and interesting presentation, and also to the audience for active participation. And hopefully, I hope this webinar will be beneficial for everybody. Thank you for your attention and have a nice day.
Thank you.